Today, we're going to dive into a really fascinating breakthrough that gets right at one of the biggest headaches in quantum computing. How do you get the right starting point for an algorithm? Well, it turns out there's a new technique that works less like a reset button and more like a super powerful noise-canceling filter. See, to get a useful answer from some of the most powerful quantum algorithms out there, you first have to feed the computer a really good starting guess. But what happens when making that guess is actually the hardest part of the entire problem? And that's where we run into what we can call the quantum tuning problem. It's this fundamental challenge that's been a real sticking point for researchers, but this new work proposes a really elegant way around it. Okay, so at the heart of this whole thing is a concept called quantum state overlap. Just think of it as how much your initial quantum state, well, overlaps with the correct answer you're trying to find. For heavy-hitting algorithms like quantum phase estimation, if your initial overlap is low, your chances of success just plummet. I love this analogy on the slide because it makes so much sense. Imagine you're trying to tune an old analog radio, trying to find a really faint, distant station. If your dial is just a little bit off, what do you get? Static. Nothing. The standard approach in quantum computing is basically like randomly spinning that dial again and again and again, just hoping you get lucky. It's unbelievably inefficient, and in the quantum world, this is a very real problem called the orthogonality catastrophe. So if endlessly retuning the dial is the problem, what's the solution? Well, this research brings in a totally different way of thinking about it. Instead of retuning, we're going to filter. Right. Instead of just throwing out your bad guess and starting from absolute scratch, what if you could take that noisy static and just filter out everything except that one faint station you were looking for from the very beginning? And this image just illustrates the whole idea perfectly. Look on the left. That's our initial state. You see that tiny little blue bar? That's our target signal, our faint radio station, but it's totally drowned out by all that noise, all those red bars. Then, in the middle, we apply this specially designed mathematical filter, and just look at the result on the right. The target state is massively amplified, and all that noise is pretty much gone. It's beautiful. So this new technique has an official name. It's called Filtered Quantum Phase Estimation, or FQPE. And believe me, it is a real game changer for how you can approach these kinds of problems. So, how does this actually change the algorithm? Well, on the left, you see the standard method. That big block in the middle, that's the main computationally expensive part of the circuit. You have to run that whole thing over and over, which burns a ton of time and resources. But now, look at the right. With FQPE, we add this new, smaller step at the beginning. That's our filter. Now, it's probabilistic, which means it might fail a few times, but once it succeeds in preparing that nice filtered state, we only have to run the expensive part of the algorithm once. That is a huge potential saving. Of course, there's no free lunch here, right? There's a fundamental trade-off going on. The more powerful your filter is, the more it boosts that target signal, the lower its probability of actually succeeding on any single attempt. So it's all about striking a balance between the power of the filter and the cost of applying it. And this quote from the paper puts it perfectly. This filtering technique really shines when you're tackling very complex problems where the main quantum algorithm is what we call extremely deep or just really costly to run. In those cases, the little extra cost of preparing the filtered state is just a drop in the bucket compared to the massive savings you get on the back end. Okay, so the theory is really compelling, but does it actually work? Let's take a look at the results from the researchers' own numerical experiments. And the results are, well, they're stunning, frankly. In their simulations, they achieved an overlap amplification factor of over 100. Let that sink in. That means they could take a starting guess that was only 1% right and filter it into a state that was nearly 100% correct. And you can see that effect right here in the data. The chart on the left, that's the initial state for a complex physics problem. The ground state we're trying to find is that tiny little blue peak, almost completely lost in a sea of other energy states. But that blue curve is the Gaussian filter they designed. And after they apply it, bam! Look at the chart on the right. The ground state is now the dominant signal, totally clear and isolated. So what does this do to the total cost of running the whole algorithm? Well, this table kind of simplifies all the complex math, but the key takeaway is right there in the second row. While the standard method's cost is super dependent on that initial overlap, the total cost of FQP is way less sensitive to it. In other words, a bad starting guess doesn't doom you to an impossibly long computation anymore. So here's the bottom line.
For the really, really hard problems, this filtering method can lead to a speedup of more than 2 orders of magnitude. We're not talking 10 or 20% faster, we're talking more than 100 times faster. It's a massive leap forward.
This is so much more than just an incremental improvement. It really points towards a future where a lot of our most important quantum algorithms are designed with this kind of filtering built right in from the start. So why does all this matter? I mean, who cares? Well, solving these specific kinds of problems is the key to unlocking major scientific discoveries. We're talking about designing new catalysts to fight climate change, creating new materials for things like room temperature superconductors, or even simulating the complex molecules we need to develop new medicines. This filtering technique makes all those ambitious goals feel much, much closer. The researchers also point to this really exciting idea for the future: iterative filtering. Think about a detective slowly bringing a blurry photograph into perfect focus. You could start with a wide, coarse filter just to get a rough idea of where the answer is. Then you use that result to design a sharper, more precise filter. And you just repeat the process, zooming in closer and closer to the exact answer with every single step. This breakthrough is like inventing a completely new kind of antenna for the quantum world, one that can finally pick out the faintest, most important signals from all the background static. It really leaves us with this tantalizing question: what new discoveries are just waiting out there for us, now that we can finally tune in and listen clearly?